The topic of this video is on nuclear magnetic resonance. What is it? How do we know? Why do we care? Particles can be defined by four quantum numbers. The phenomenon of nuclear magnetic resonance, or NMR, takes advantage of the spin quantum number s. So to understand NMR, we need to discuss spin. To understand spin, we will compare it to angular momentum we experience in the macro world. But this is not to be confused with the angular momentum number L. And so for the purpose of this explanation, we will completely ignore these other three numbers and focus just on S. In classical physics, a spinning object will create angular momentum represented as a vector in the direction of the axis of rotation. It was observed that protons produce small magnetic fields, and from Maxwell's equations, we know that magnetism is produced by a change or movement in charged particles. We also know that protons are charged particles, which implies that they are moving or spinning to create this magnetism. This moment vector, created by the magnetic field, is similar to the angular momentum vector L, as it also points along the axis of rotation. In order for the magnetism to exist, the proton must have angular momentum, but again, protons are not actually spinning because they're just a point object in space. In the atomic world, things are too small to spin, but they do appear to have an angular momentum. However, this is the most concrete, relatable way to describe the value of S, and you can think of it as intrinsic or innate momentum that exists as a fundamental property of the particle. Consider the hydrogen atom. Its nuclei contains a single proton. We now know that this proton has a spin, and this spin creates a magnetic moment. Now that moment can spin one of two directions, either up or down, and they're denoted by +1/2 or -1/2. Turns out that of the two options, the +1/2 state is favored and therefore of a lower energy. In simple terms, you can think of the -1/2 state as facing against some external magnetic field and therefore requires more energy to do so. To review, spin does not mean rotation. It is simply a property of matter that exists in certain states that we assign somewhat arbitrary numbers to differentiate. This spin creates a magnetic moment that interacts with other magnetic fields. The value of the spin is quantized and can only exist in certain states with no in-between. And in the case of the proton, these states are +1/2 and -1/2, with the +1/2 being favored. Back to the dreidel or top analogy, when a spinning object is subjected to a gravitational field, a torque is applied that causes the object to rotate about its axis parallel to the gravitational field. This is called precession. The magnetic moment of the proton similarly interacts with magnetic fields, and if it's in a uniform magnetic field, it's going to not only have its own inherent momentum, but it will also precess around a different axis that is parallel to the magnetic field, similar to a top or a dreidel in a gravitational field. We know from Planck's equation that the energy of a photon is related to its frequency. Also, Peter Zeeman showed that the energy difference between two spins is proportional to the magnetic field that they are in. So the stronger the field, the greater the energy differences between them. Now, if you rearrange these equations and combine them, you end up with this strange result. This is known as the Larmor frequency of precession. This equation describes the precession of protons in a magnetic field, and this symbol is known as the gyromagnetic ratio and is constant for a given particle. What this means is that the frequency is directly proportional to the strength of the magnetic field that the particle is in. Since humans have the ability to create and control uniform magnetic fields with varying strengths, the implication is quite interesting. We can make particles dance as fast as we want. So far, that covers the nuclear and magnetic of NMR, but what about resonance? When you push your friend on a swing set, the energy from your push is transferred and the velocity of the swinger increases. You have to push at or near the same frequency of the swinger for efficient energy transfer. Otherwise, you'll push on empty space when the swinger is away from you. This is the concept of resonance, matching something's natural frequency to add energy to the system. Now, we know that these particles' spin states can exist in two energy levels. We also know that in the presence of a magnetic field, protons and other particles precess at a certain frequency. What if an electric magnetic wave at the same frequency were applied? Could we increase the energy of the system and cause a spin orientation to change? This is the fundamental theory behind nuclear magnetic resonance and was proven through experimentation. The first person to experimentally prove the existence of NMR was Isidore Rabi. At this point, the magnetic nature of particles and the properties of spin was known. He set out to prove that the spin of a particle could be flipped by adding energy through electromagnetic waves. And so you have this beam being focused at this detector, and there's a constant stream of protons going through there. Now, if NMR is correct, we can add a radio frequency signal that matches the resonance of these particles, and it should add energy to the particle and cause them to flip. And so if a spin down particle is following this path and it goes through this beam, and if it does flip, then it would be a spin up. And if it's following this path, then now the spin up would get attracted to the magnet and it would not make it to the detector. And likewise with the spin up, if a spin up is following this path, it's going to then come down after it gets repulsed, and then it's going to flip to a spin down, in which case it's going to get attracted to this positive side. And so Isidore postulated that if a reorientation of spin occurs in this field, the subsequent conditions in the second deflecting field are no longer correct for refocusing, and the intensity at the detector goes down. And what this means is that if these are flipped, then some number of these particles are going to get pulled away from the beam, and the beam's not going to be as strong. So the results of the experiment were exactly as predicted, and due to practicality reasons, it's easier to change the magnetic current in these magnets than to change the radio frequency in the frequency coil. And so if you're changing the current in these magnets, then the frequency of these protons is going to slowly change. And once it reaches the same frequency as this constant signal, then you should have a resonant frequency and there should be a flip. So as they increase the current in the magnets, the frequency increases, and it is seen here that this right here is the resonant frequency where these particles are flipping and veering off. And just like that, NMR was proven.